Section 33 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy, Chapter 22. The Motions and Brightness of the Stars. The term fixed star, which has survived from ancient times, we have already found is but relative, and that all stars have some motion. If the position of one of these so-called fixed stars is noted by observing the time and height at which it crosses the south point in the sky, and this observation is compared with accurate records which we have, going back nearly 200 years, it will be found that quite a number of the stars are moving slowly across the sky. This movement is termed proper motion, which, as seen from the Earth, is at the best an exceedingly minute quantity. Thus one star, and that the most rapid, has moved about the diameter of the Moon in the last 300 years, or an amount which the telescope is quite incapable of detecting. It may be said in passing, however, that the actual observation of fixed stars from the Earth after an interval of, let us say, 100 years, would show more difference. Yet this is due, not to the motions of the stars, but to alterations in the direction of the Earth's axis, and other causes which give apparent and common motions. The maximum proper motion is that of the 8th magnitude star, number 243, of the 5th hour in the Cordova Zone catalogue. The star has an apparent drift of 8 seconds, 0.7 annually, which would carry it round a circle of 360 degrees in 149,000 years if it moved uniformly at its present rate. This amount can be appreciated when it is stated that 2 centuries would be required for a change in position equal to the diameter of the Moon. Arcturus, since the time of Ptolemy, has moved more than a degree, and Sirius about half as much, the motions of these 2 stars having been detected first by Halley in 1718. In fact, the late Professor Newcomb says that if Hipparchus or Ptolemy had made exact determinations of the positions of the stars and today should rise from a long sleep, Arcturus would be the only star in which they, or the priests of Babylon for that matter, could detect any change in position relatively to the other stars of the heavens. There is no case in which this quantity is as large as a foot rule seen at a distance of 50 miles. And for comparatively few stars is this motion certainly appreciable. Notwithstanding the extraordinary degree of precision that has been obtained in recent measures of parallax, for a satisfactory solution of the problem we must probably devise some new method of using the spectroscope or some other instrument for determining proper motions. The study of the proper motion of the stars indicates that, on the whole, the stars are opening out from a point near Vega and closing in to the opposite point. Professor Kapteyn finds that the stars may be divided into 2 great classes, having on the average proper motions quite different in direction and magnitude, and that these 2 systems are moving through each other, one from a point in the south of Hercules and the other from a point in the Lynx. In the latter class the solar system doubtless belongs, for it seems to be traveling toward that portion of the heavens occupied by Lyra. The problem of determining the actual speed of travel involves not only a knowledge of the proper motions, but also of the distance of the stars. The latter quantity, as has been seen, is obtained by noting the change in position, or parallax, and is known for about 100 stars. The motion in the line of sight can be measured by spectroscopic methods, employing Doppler's principle. The rate of travel of stars through space has thus been ascertained to be about 10 or 20 miles a second. How is it known that stars are moving in the line of sight? Millions and millions of miles away a star may be approaching the Earth, and yet through the telescope there is no change of position and no appreciable change in magnitude. But here use is made of an ingenious principle which takes its name from its discoverer, Christian Doppler (1803 1853), a physicist of Prague, who made an experiment with quite another object in view. Placing some musicians on a railway car and taking his stand on the platform, he noticed that the pitch of the sound was raised as the moving train approached him, and was lowered after it had passed and was receding. If this could happen in sound, why not in light also? Although the vibrations occur infinitely faster, so that the color of a luminous body, equivalent to pitch in sound, would be affected by its motion. In 1868, Sir William Huggins successfully applied Doppler's principle. If a star is coming toward us or receding, there occurs a displacement in the spectra of the manifold light waves, varying from the fundamental value of the velocity of light, 186,000 miles a second. When a star approaches, the light waves are crowded together. When it recedes, they are drawn apart. Now, as the number of the vibrations of the light waves and their length determines the color of the light or the position of the waves in the spectrum, by microscopically comparing spectrum photographs of the same star and noting the displacement of the Fraunhofer lines, it can be determined whether that star is approaching or receding. Doppler's law has been explained very simply by Professor Edgar Larkin as follows. In the diagram, Fig. 42, A is a ray of light from the star S falling on the side of the prism P, which has the property of separating any mixture of light into separate waves. Light from the sun or stars is made up of a vast number of colors, all appearing between the limits red and violet. Had the pencil A not encountered the glass, it would have passed to B, but the prism separates the white light into colors which can be projected on any white surface. The red is invariably bent out of its original direction the least, the violet most, and will respectively pass to R and V, with every other color between. The shorter the waves, the greater their deflection from a straight course. Red waves run 33,000 to an inch, and violet 64,000. An eye at E would see all the colors between R and V direct, and at H by deflection, if a screen is allowed to receive the light from R to V. Solar and stellar spectra are crossed at right angles by black Fraunhofer lines. Take any one, say F, anywhere in the spectrum, and measure its position with a micrometer. Then the eye, either at E or H, would see a spectrum as outlined in the upper diagram of Fig. 42, extending like R, 1, F, 2, T, V. Let the prism move at great speed, such as that due to the velocity of the earth, toward the star, or let the star move toward the earth, then the line F will move to 2, or toward the violet end. But if the earth and stars move in opposite directions, the line F will move to 1, or toward the red. After the more brilliant stars of the heavens have been identified and their positions determined with as much accuracy as possible with the methods of observation and instruments available to the ancient astronomer, the next development was to compare their relative brightness. In 134 B.C., at the time of Hipparchus, a catalogue of stars was prepared which was said to have been suggested by the sudden appearance of a new star in the constellation of the Scorpion. The stars were divided into 6 magnitudes according to their brightness. The catalogue of Hipparchus, containing as it did 1,080 stars, has since proved most valuable to astronomers. Next came Ptolemy's great Almagest, published in 138 A.D., which contained a catalogue of 1,028 stars, doubtless based on that of Hipparchus. Ptolemy used a scale of stellar magnitudes which has continued in use to the present time. The brightest stars of the sky, such as Sirius and Arcturus, were regarded as of the first magnitude, and the faintest visible to the naked eye the sixth. Today a small telescope will render visible stars down to the 9th magnitude, of which there are over 100,000. Ptolemy employed the first 6 letters of the Greek alphabet for this purpose, and then subdivided the classes he made. If a star seemed bright for its class, he added the Greek letter mu, standing for meson, large or bright. If the star was faint, he added epsilon, standing for elason, small or faint. These estimates were carefully made. If Ptolemy's original manuscript were at hand, his magnitudes would be useful to modern astronomers in determining the secular variation of the brightness of the stars. But the errors in the various copies and transcripts of the Almagest, which have come down to modern times, are so great that the positions, magnitudes, and identifications of about 2/3 of the stars listed are uncertain. Indeed, the oldest manuscript of the Almagest dates only to the 9th century. The Persian astronomer Abd al-Rahman al-Sufi (903 to 986) reobserved Ptolemy's stars in 964 A.D. and noted cases where he found a difference. This work survived in Arabic, and translated into French by Chalerup (1874) is available for modern astronomers. Ulugh Beg, who flourished about 1450, also published a star catalogue based on Ptolemy, but with careful measures. In 1850 Tycho Brahe published a star catalogue containing the records for 1005 stars. A supplement carrying this to the South Pole was added by Halley, who went to St. Helena in 1677 for the purpose of making observations of the southern heavens. In 1690 was published a catalogue by Hevel, in which several new constellations were added, and which was of interest as containing the results of telescopic observations, so that stars invisible to earlier astronomers could be added. No important additions to the knowledge of the brightness of the stars was made until Sir William Herschel, the greatest of modern astronomers, brought his powerful telescopes to bear on the heavens. He found that when two stars were nearly equal their difference could be estimated very accurately. He adopted a new system for denoting this difference, using points of punctuation, a period denoting equality, a comma, a very small interval, and a dash, a larger interval. From 1796 to 1799 he published in the Philosophical Transactions 4 catalogues which covered 2/3 of the portion of the sky visible in England. 2 other catalogues of his, preserved in manuscript, have not yet been published. It is interesting to know that these observations of Herschel's were reduced at the Harvard College Observatory under the direction of Professor E. C. Pickering. Herschel's magnitudes for 2,785 stars, observed over a century ago, have an accuracy nearly comparable with the best work of today. His work stood unexcelled for nearly half a century, for no astronomer was wise enough to see how much would be gained merely by repeating such observations. Had observations been thus repeated every 10 years and extended to the southern stars, many valuable data as to the constancy of the light of stars would have been obtained and our astronomical knowledge greatly increased. In 1844 Argelander proposed to modify Herschel's method by using numbers instead of points of punctuation to denote the intermediate brightness between the various magnitudes, a method known by his name. His catalogue, the great Bahn-Durchmusterung (1799 to 1875), contains as many as 324,198 stars visible in the northern hemisphere. After mere judgment with the eye, it was but natural that some more accurate means should be employed, and various photometers, to which we have referred elsewhere, were eventually adopted for the purpose of gauging stellar brightness. In 1856 Pogson showed that the scale of magnitudes of Ptolemy, which is still in use, could be nearly represented by assuming the unit to be the constant ratio 2.512, which has been adopted as the basis of the standard photometric scale. Thus an increase of 4 units in number would express the magnitude corresponding with a division of the light by 100, and a 6th magnitude star would have but 1/100th the brightness of one of the first magnitude. Photometric observations have been undertaken for many years and are now in progress on a large scale at Harvard University, at Potsdam, and at Oxford. Various forms of photometers are employed. Simple photometric work takes into consideration only the total light of a star insofar as it affects the eye. This light may consist of rays of many different wavelengths. In red stars one color predominates, and in blue another. Hence the preferred method is to compare the light of a given wavelength color in different stars and then to determine the relative intensity of the rays of different wavelengths in different stars, or at least in stars whose spectra are of different types. The brightness of the stars may also be measured in a simpler but less satisfactory method by determining the total light in a photographic image, a method open to the same objection as eye photometry. In other words, the rays of different colors are combined and affect the photographic plate differently. Consequently blue stars appear brighter than the red. Still photographic photometry is extensively used, and various proportions and corrections are employed so that satisfactory results are obtained. As a result of modern methods of classification, the number of stars of the first 6 magnitudes visible to the naked eye is about 5,000. These are grouped in the following order: first magnitude, 20; second magnitude, 65; third magnitude, 190; fourth magnitude, 425; fifth magnitude, 1100; sixth magnitude, 320. It has been estimated that over 100 million stars are visible within the range of present visual and photographic instruments. The first magnitude stars number only about 20, and on account of their conspicuous brightness serve as landmarks in the study of the heavens. Their names, constellation, magnitude and color are given in the following table, listing first the star name, followed by the constellation, followed by the magnitude, followed by the color. Footnote: when a star outshines a star of the first magnitude, it is no longer possible to designate its brightness by 1. Hence the numerical expressions 0.2, 0.3 and -1.4 in the foregoing table. End footnote. Star, Sirius. Constellation, Alpha Canis Majoris. Magnitude, -1.4. Color, bluish-white. Arcturus, Alpha Bootis. 0. Orange. Vega, Alpha Lyrae. 0.2. Pale blue. Capella, Alpha Aurigae. 0.2. Yellowish. Regal, Alpha Orionis. 0.3. White. Canopus, Alpha Argus. 0.4. Bluish. Procyon, Alpha Canis Minoris. 0.5. White. Betelgeuse, Beta Orionis. 0.9. Ruddy. Also Betelgeuse, Alpha Centauri. 1.0. White. Arcanar, Alpha Eridani. 1.0. White. Altair, Alpha Aquilae. 1.0. Yellowish. Aldebaran, Alpha Tauri. 1.0. Red. Antares, Alpha Scorpionis. 1.1. Deep red. Pollux, Beta Geminorum. 1.1. Orange. Spica, Alpha Virginis. 1.2. White. Also Spica, Beta Centauri. 1.2. White. Also Spica, Alpha Crucis. 1.3. Bluish-white. Fomalhaut, Alpha Piscis Australis. 1.3. Ruddy. Regulus, Alpha Leonis. 1.4. White. Deneb, Alpha Cygni. 1.4. White. In connection with stellar photometry, it has probably occurred to the reader that photographic charts would prove very serviceable, as the brightness of the photographed image could be used. Such indeed is the case. Astronomers interested in stellar photometry have devoted no little attention to the study of these charts and plates. End of section 33.